Okay, we are live. Yep. With Tara today.
Hello.
Um, so we were just talking about today might be a good day to kind of do a. Normally we'll try to build stuff on stream, but I've been doing so much between streams. Seems like it takes half a stream just to go over what done. And I did a lot since the last one, so might as well make this whole thing a catch up and then also a roadmap. What next? Since it's been a month now, it's now February. Yeah. How does that sound?
That sounds great.
Right. Where do we start? I guess we can start with where we left off in the last stream, which was trying to get bindings to work, but maybe before get into that, I'll just give an overview of what's going on here. A year ago, built a we were just talking about fantasy consoles, so I could almost call it like a fantasy operating system, but kind of an experimental Unix-like development environment that was in the browser. It was pure WebAssembly, and it was kind of a proof of concept and demo where you go to Wanix.sh and watch the last demo that we did at WASM.io. And it gets in all kinds of crazy stuff. But and it looks like some people have been trying to actually use it. There was some issue they call, and it's that damn part that that tool chain stuff that kept breaking that Julian was working on. Remember that?
Vaguely, yeah.
Anyway, whatever what's in the repo right now is that old version. Oh, I thought I put a link saying that we're working on a whole new version 03 in another branch. So this is what we've been working on this last month. And we're basically starting over from scratch. And one of the main things that's different is it's built on this idea of Plan 9. Well, Plan 9. Plan 9 is an old operating. It's kind of the successor Unix from Bell Labs. And it sort of leaned into some of the ideas that Unix introduced, but sort of simplified and refined. And it had a lot of cool ideas that we just don't have today. There's sort of remnants, like little bits, like the proc file system in Linux. If you go to /proc, you can, not a file system in that it's storing files. It's actually an interface to information about the running processes. The Plan 9, that's where the idea came from. They kind of did everything with the file system. And so that, Linux as an operating system has something like 400 syscalls, sort of API, system API. Plan 9 had like 40 syscalls. Half of them had to do with the file system. Half of them had to do with managing processes. and a lot of the rest of the kernel API was exposed through the file system. You'd use the file system to work with networking, etc. And so it also had this idea of namespaces, which eventually sort of evolved into the idea of truths and jails, which is kind of what influenced containers, Docker. So all these really great ideas were in Plan 9, and based on this kind of simple architecture of, oh yeah, so I guess some people are finding out that there's been a rewrite, and so yeah, finally kind of explaining it. This is kind of a good stream to just get a good overview of what's going on. And we're doing, even though we didn't finish our little poster or whatever, but in our Discord on Friday, we're going to have a Plan 9 watch party to learn more about Plan 9. And Plan 9 also has namespaces, which is every process runs in its own namespace, which is basically what they would call file system. So instead of your file system being this monolithic thing that every process kind of sees the same thing, like Docker, like containers, what's running in a container sort of has its own file system. And that's how Plan 9 worked. Whenever you create a new process, it would run in its own namespace with its own file system. And because the file system was how you would interact with, the system, you could add and remove, basically giving you capabilities. You could add and remove capabilities that a process can have. So if you don't want the process to do networking, you would remove the networking file system so that when the process runs, it won't be able to access the file system that lets you work with networking. And then you can add custom stuff, and all these things fell out of it, which are sort of just like really cool things that I wanted to try and make accessible through Wanix. So another reason for this rewrite is because it felt like Wanix was cool enough to not be browser specific. It's great that we can do all this stuff in the browser, but I'd love to use it outside of the browser to do Plan 9 things on Mac OS and Windows and Linux. So really at the heart of this was this Plan 9 style file system, whatever. So first half of the month, we were just doing file system stuff in Go, just trying to get some abstractions and tooling to make it easy to build file systems. And then we finally got to, a file system in the browser that was doing interesting things like setting up other file systems, so like a meta file system, and namespaces. And then another big difference between the original Wanix, in which we created a custom shell because we had to compile everything a certain way to compile the WebAssembly. And it was on the roadmap, but we didn't initially support WASI, so that's a sort of a standard WASM executable format. It's not really a format, it's just using the WASI. It's a standard interface, so a lot of executables a lot of programs that compile to WebAssembly will be compiled to WebAssembly using WASI. And we didn't support them for certain reasons, but now we will. But then there was also the idea that you can't compile everything to WebAssembly. Some things are too complicated. Some things, there's too many constraints. So wouldn't it be cool if you could still run x86 binaries? So some other work that had happened since then, we started working with V86, which is a an emulator. It's an x86 to WASM JIT, so it's very fast. Probably the fastest x86 emulator in the browser these days. And it can run all kinds of stuff. You can play with Plan 9 just in the browser. It works on your phone. Well, you can use it to play with old Windows if you wanted. Is this how Windows booted? I don't remember. It's sort of self. When Windows 2, actually Windows NT, they added a whole bunch of stuff, kind of being actively developed, which is these are all not booting from save states. Here we go. Oh, the audio. Anyway, look, it's Windows 2000 in your browser. So, you know, when Apple transitioned from, I mean, they transitioned CPU architectures a couple of times, but obviously the last time it was to Apple Silicon. And in order to support old programs that were for Intel, they have this subsystem called Rosetta. And Rosetta is basically an emulator for x86. And so even though things run a little bit slower, you can still run x86 stuff on Apple Silicon. And I thought, well, what if we had that for WebAssembly? So if Wanix had an emulator like v86 to run x86 programs in Wanix. And so that led to a bunch of stuff we did called NV86 and video on that somewhere. But basically, I was trying to make some tooling to make it easier to work with v86. So now the idea was, instead of, at some point I realized we could make Wanix even simpler if we don't include a shell. If we're gonna bundle in this VM, basically a VM, why don't we use the Linux shell as the shell for Wanix? Because if the Wanix system API is now just a file system API, you can use that from any platform, because it's a sort of a universal API. In fact, WASI, which is sort of an incomplete standard in terms of what kinds of stuff you have in libc or syscalls. For example, you can't work with sockets. Well, you can read and write against sockets, but you can't create a socket. Stuff like that. You don't have signals, blah, 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 blah. But they do have file system API. It's like file systems are everywhere, pretty much the same rough API. And so if Wanix sort of if you could do everything in Wanix through the file system API, it becomes this kind of like universal meta operating system. And then if it has a VM built in, it's sort of this like hypervisor where it can, create virtual environments and yada, yada, yada. But initially, to bootstrap, it would have its own, it would use the VM to give you a shell to interact with Wanix. So we're trying to build that up from scratch, and it started with the file system stuff. And one of the coolest features of Plan 9 was binding. So Linux file systems, you can do linking and symlinking, but Plan 9 had something slightly different called binding. And if you do a bind mount on Linux, that's kind of the idea, except Plan 9's was a little bit more powerful. For example, you could bind mount a directory on top of another directory, and it would merge them. So you'd get this sort of union file system. So yeah, let's now, I guess, get to the point that we left off in the last stream. So we'll kind of review. We have this Wanix object here on this effectively blank page, and it's more or less just a file system. We have some helper functions in here that we use from. So the idea is, how do we bootstrap into that shell where we can work with this file system, this Wanix file system that is the Wanix system. It's very recursive and meta, but so for now, we're sort of working in the DevTools console since we don't have a shell yet, so bootstrapping it. So here's what the file system kind of looks like right now. We've got the file system, which is how you could create new file systems. So right now in the browser, there's actually two native file system APIs. They're actually the same API, but one of them lets you open up a directory on your host computer and expose that to the page, and then and then JavaScript on the page can actually work with your host file system. And then another called OPFS, which is Origin Private File System, basically like local storage, which is a domain-specific, persistent storage in the browser, but it's actually a file system API. So that's perfect. We're working with file systems. So this, it looks like we actually made a file system. What's this one? Type, yep. So in Plan 9, it's very common to have these control files that you can send messages into. They're basically like little command line utilities, but the way you work with them is you write to them via the file system as if they're a file. Write commands into it, and then it does stuff. That's how you're able to do more things with through the file system as an API. So anyway, we'd send a message to control to mount it, and then it does that. But kind of that on setup now. I don't think there's anything in this because but basically this is now an interface to the Origin private file system on this domain, localhost 8080. We could write a file into it. And now there's a file there. We can read it. So a lot of the file systems we've made so far are not really about storage. They're kind of like interfaces to things. But this is sort of one of the first file systems that actually lets us kind of create normal files. So there's Hello World. And there's also a OPFS right here because I basically did a bind. So it's like a link to say, let's create a directory here called OPFS, but it is literally this directory. So if we look in OPFS here at the root, we've got our file. So you can do this not just for directories, but files as well. And the idea was, and I don't know if Plan 9 does this, but the idea was to use that to do interesting things. So really quick, there's this DOM file system. And this is, we're in the browser. So here's kind of an example of a file system representing an interface to, in this case, because we're in the browser, some stuff on the DOM. So we could create new elements. Right now we have these kind of like built-in elements. We have reference to the body that, of course, a page will always have. And Xterm is sort of a special one that we added a couple streams ago, maybe last stream, that creates a Xterm JS element on the page. So we'll make one of those in a minute. But first, there's also this style, not a directory, but a file. And so just as an example, we could write to DOM style and some CSS like body, background, color, red. Yep. Write that to DOM style, and right, it applies it to the page. So let's make Xterm. So this is one of the patterns in Plan 9, whether you're like creating a new TCP socket or a new whatever, they would have this pattern of, they called it the clone dance, because the file would normally be called clone. But basically, it's sort of like first you allocate a thing by reading a file. You're trying to do all of this through the file system, which means, and one of the benefits of the file system is now you use normal shell commands, but we don't have a shell yet. But we have these commands. So for example, we can read DOM new, and we'll do Xterm, and it returned 1. 1 is now a directory in DOM, and it's basically our Xterm element. But we don't see anything because just like if you were to do create element, in JavaScript, it's not going to show up until you attach it to the body. So we do have body here, and it has a control file. So if we write that control file, append child, it's almost like object-oriented programming. We're calling a method on the body, and we'll append 1. That's the DOM resource that we're referring to. There we go. We've got now a terminal. And this terminal element is a little unique in that it has a data file. And that data file is basically an API to the data of a terminal, because a terminal, we talked about this before, is actually a terminal emulator, and basically a way to receive keyboard input and send it somewhere. And then when somewhere has output, it sends it to the terminal, and it can, part of being a terminal is supporting certain escape codes and all of this. But for the most part, it's just like input and output. That's textual. So if we were to write to DOM, hello, we get hello. And if we were to read from it, anything that we type here would show up there. This was one of the things that we're getting to that we ended in the last stream, because when we originally implemented this, it was not a stream. It was basically it worked a lot like these type things, where it's basically a virtual file, and it just contains some bytes. And so we made a way to make those in in Go. This is all written in Go for various reasons. Um, Whereas with data, it's actually kind of a stream. So if we were to read from it, we wouldn't just uh, get some fixed bytes. It would actually continue to read indefinitely. It's a stream because it never ends. We could keep typing. So that's one of the places that we stopped at. We'll look at the source for that in a bit, but then also this terminal doesn't actually do anything, and we were talking about B86 and stuff. So we also have might have noticed, nope, oh, there's this VM file system, and we can use that to do a clone dance. VM new. Oh no, we're bottom of the screen. Okay, so now there's we have a VM with an ID of 1. Let me just. All right. And this is a very initial pass. This VM interface, will eventually let you control state of it and snapshot it and load previous state and all this stuff. But for now, it's just basically all it does is support starting the VM. So you allocate it, and then you would send a message like write VM1 start, basically running the start command on it. But how would we interact with that VM? It's just sort of this thing in the background. What we want is to wire up this terminal to it. And the idea was we could use binding to do that. So the idea was, what if we were able to create a file here that it will read and write to for its console? Because then we could basically do a binding that points to the data file for this terminal, and then that's how we could wire it up. And then that's a general pattern, is a way that you can wire up different systems just using the file system. So the way we would create a binding actually through the proc file system, because we're actually doing all these operations. So the proc file system here is very different than the Linux proc file system. Similar that you can actually, every process you can reference here. And we can self to see what process we're running as. And so here we're running as 1, this process, and pretty sure this is, So processes normally are kind of units of execution. It's like a primary abstraction of an operating system, thing that, programs run as, and then, shares the CPU. Wanix Wanix processes are abstract. And this is because I wanted to support, when you're in the browser, a process is something that runs in a web worker, maybe. When you're on a native machine, you could have a native process that represents, a process on the actual host operating system. So processes are abstract here. They have a process model that would be the same as kind of POSIX processes, with arguments, environment, standard inst, all that. But the way they're actually implemented, there could be different kinds of processes. And right now, since we haven't really gotten into that, the only type of process is namespace, which is the Plan 9 idea of a namespace. So every process gets its own namespace, which is a view of a file system that can be customized to, again, expose or hide capabilities of the system. If we were to look at NS here, this is the namespace that process 1 has. And it looks just like our root, because it literally is. It's kind of a recursive thing. We could just keep going here. Proc 1 NS. Oops. Yeah. But if you set up another process that has a different namespace, then this would be different. But it also lets us kind of, as sort of the root process or administrator, I don't know, we can actually like manipulate the namespaces for different processes. This is the sanity check. Tara, is this you're kind of following for the most part?
Yeah, I think so.
So process. So we don't implement any web worker stuff yet. That's sort of on the roadmap. But we had to implement the process. Basically, it's almost like an empty process just to create a namespace, because that's what we're working with, and that's why there is proc1, because that's basically what we're using when we run all of this. So we're actually using namespaces already. Bindings is what we're trying to get to, where we left off, is a feature of namespaces. So there is a control file for this process, and we can write to it and bind. So this is, again, a way to create extensible syscalls, right? In Plan 9, bind was a syscall. You'd have your file system stuff, API, you'd have your process management stuff like fork, deck, and then you had bind. Wanix is maybe even more Plan 9 than Plan 9 in that you do everything through the file system, and things like these control files. So, which means, again, you could do everything through the file system. Bind. So let's see. As an example, as a quick example, kind of recreate this binding. So really, that's our file system. Here, we look at mount. That's kind of where the data for that file system is. To set up it as a root directory called OPS. So we could kind of do that again. I'll call do proc1 bind. We fsys 1 mount, and then create a binding at opfs 1 2. Okay, now we can list here. We have opfs2. We look in opfs2 file. So where we're trying to get to was we have this data file that represents kind of a data line to the terminal that we have here. We want to wire it up with a VM. So the idea was, what if we made it so the VM tries to read from a file that exists in its directory in here. In this case, in a Linux terminology, TTY S0, which means usually a terminal or console over the serial port 0, the first serial port. The common way for VMs to expose console over something other than just on the display. And so could we wire that up? DOM1 data. Wire that up with VM1, and we'll call it TTY0. Okay, now when we list here, we have a TTY S0. So now, finally, when we start this VM, VM1, start it. It boots a machine. We see it's booting Linux, Linux kernel here. A little slow. It's booting. The emulator is not this slow. Part of why this is seems kind of slower is some details I won't get into, but which is part of why we're getting these handler violations. So this takes a minute. This VM is based on an Alpine image that is being served over file system, file server, or HTTP server. But it's kind of a whole Alpine system. And now we have a terminal. And then the idea is, of course, that we could run x86 programs in here. This is a full x86 emulator. But we can also then interact with Wanix. Hey, it's our file system. OPFS2 is in there. That file. So the idea is basically everything we've done so far would be part of the bootstrap process that Wanix would have to get you to a shell that you could then use to manage, do more stuff with Wanix, all through the file system using things like cat, ls, and we don't have to create a custom shell that re-implements all of these common commands like copy, move, it's all just there. This is not fully implemented. We can't write files. Basically, I had to create a bridge, which I'll talk about. Well, I guess I was going to show a little bit of the code for getting this binding. We're already 40 minutes in.
Time flies.
First. So let's see, where are we? This is the 03 branch. I have pushed all these changes to the but they will be. So the basic idea is, so VM, we've got, where I put it? I guess I put it. So earlier streams, we developed a bunch of Go stuff to be able to write file systems. So the VM file system is implemented here. To implement a file system, you just have to implement open. We've added open context as a thing that you can use for various reasons so that we can actually pass kind of state context information in there as well. And we built all of these kind of utilities to easily build up file systems. So mapfs is a file system based on a map where, you know, a string is basically the file name or file path, and then the value is another file system. So you can kind of like compose or multiplex file system using mapfs. OpenFunc is a utility that very similar to handler func for HTTP and Go, where you can pass it a function that implements open, and it'll return a OpenFunc. Oh, that's part of the thing. But basically, it implements open, the file system API that satisfies the FS interface. And so then, func file is a way that it implements a FS file that is sort of defined by functions. So we have a read func. So this is called when you read from it. This is how we implement the clone dance when you read a new and you get back a resource ID, basically calling this. And we had to create some other utilities too, mapfs, unionfs, which is basically if you have multiple file systems, this will kind of combine them or merge them. So if the root is a directory, they'll all have all of their directory entries are all combined. And so here we're creating a union from this mapfs that we made, combined with resources that we're creating. So resources are just string to file system. So it's actually implementing the mapfs type. So we just kind of pass it to a mapfs, do a union. So that's how, we can define specific dynamic files, but then also have, the 1, 2, 3 of all the resources that you create. When you create those resources, for each VM, they also implement open. There's a file system here. Here's the control file for this file system that we wrote to with start. And most of the heavy lifting is done in JavaScript. Starting v86. But what we wanted to talk about was using this tty s0 file. So before we start, we check to see if this tty s0 file exists. If it does, then we open it. And then Go has IO copy, which is basically it will continuously read from a reader and write to a writer, like piping data. We run this in a Go routine. It runs in the background continuously. So basically, we're saying we want to read from this tty s0 file and pipe it into our serial, which we'll look at in a minute. And if tty implements writer, then we'll do the same. We'll read from serial and then write into the writer. So bidirectional copying of data. And this file just happens to be the terminal data line. And so we're basically wiring these up. Serial is implemented here as a, in order to work with IO copy, we need to implement the reader and writer APIs, which is just read and write. And then in those, we implement some code that will use the JavaScript API to actually get bytes in and out of the emulator. So for example, there's an event-based interface, add listener, serial 0, output byte. It's kind of annoying. This is why it's slow. It does 1 byte at a time. We call this passing. Go ahead.
I just said oof, 1 byte at a time.
Yeah. That's why it's kind of slow. I wish there's another way that we could do this, but this is what works for now. Because this is event-based and we need to kind of implement read, the way to do that is to basically accumulate these bytes into a buffer, and then we can read on that buffer. So that's what we do here. Set up whenever we get a byte, we write into this buffered pipe. And so then when we call read, we read those bytes off. And then write, we're pretty much just calling serial send bytes onto serial 0. This is basically how you call JavaScript from Go in WASM. We do have to kind of convert the bytes that we get here into a uint8 array. With this helper, which I'm not entirely sure, basically just copy bytes from one context to another. So now it's effectively the serial port of the VM now has a read-write interface. So we can use that to basically use IO copy to work with this TTYS0 file, which on the other end, we set this up before. Data used to work kind of like func file, but now it needs to stream data. So we kind of do the same thing here. When we set up xterm, it has an event listener whenever there's data, and we basically put that into a buffered pipe. And similarly, when we write to it, just have to call write to the xterm JS JavaScript object. Basically, making both ends implement the IO read and IO write interfaces, which then lets us use IO copy. So that's kind of the thing that I implemented since the last stream, but I also did a whole bunch of other stuff. Part of it is trying to get this file system inside Linux in this emulator to bridge to the Wanix file system. We do this, patch some x86 source. We look at how we instantiate a v86 emulator in JavaScript here. We tell it where the v86 WASM is, we set up its memory, give it a tiny little BIOS and VGA BIOS and some other config stuff. Defining this file system is where we're serving the Alpine file system, which is we're basically serving it over HTTP here. There's a JSON. This is a v86 specific thing, but there's a file system JSON, which is just a JSON file of basically an index, kind of inode data, so all the metadata. And then it points to every file name. Then there's like a hash, and then there's this big directory called fs with every file renamed to the hash of its contents. So it's kind of like content addressable. And v86 will, as you request files on the file system, it will download them over HTTP as needed. Kind of a neat feature for an emulator. Normally an emulator, you have to give it an image of a disk or something like that. But they implemented this kind of neat feature to stream in files over HTTP. They did this with this 9p, which comes back to Plan 9. In Plan 9, everything was done through the file system. And so you only needed one protocol, and they called it 9p. And it's basically like a remote file system protocol. And it's commonly used by virtual machines and emulators to mount the host file system inside the emulator. And so because of that, it's built into the Linux kernel. I think it's built into Mac OS, might even be on Windows. because as those systems get virtualization, 9p is such a common protocol. So this command line is basically the arguments that you pass to the Linux kernel. And you can, when you do that, you can tell it where to get the root file system from. So there's this host 9p thing that is a virt.io device. So normally 9p is a network protocol, but these v86 hackers basically implemented a virt.io, which is basically a way to create virtual interfaces as devices, as if it were a physical device on the PCI bus or whatever. So it's basically a way to interact with 9p, but not over the network. Then in JavaScript, they implement a 9p server that then converts everything to HTTP calls. And so I felt like that's a great place to bridge into the Wanix file system. And then real quick, what does that look like? So this is the 9p code that comes with v86 that I had to patch here, but most of it's pretty much the same. So they're implementing the 9p protocol, which is, file system stuff. It's a little tricky. And it's specifically 9p 2000L, which is a variant that supports Linux specific stuff like symlinks. But it's implemented as a virt.io device. And so there's a bunch of stuff here that has to do with like defining a device that this virtual machine emulator needs. I don't know how any of this works, but ultimately it gets to a point where once they've implemented all that device specific stuff, they just have to implement 9p as if it were over the network, except it's not over the network. So all that comes down to receive request. So whatever the bytes, the request coming in, and then like any file, almost any protocol, you just implement something to handle the request coming in and send it back out. 9p requests, they're binary format, and so it's basically a big switch here for every type of message. You can kind of see the semantics of the 9p protocol. There's statfs, there's topen, link, symlink, make node. So these are all the different Plan 9 message types. And they're doing a bunch of stuff that I'm like, this is pretty crazy, but they have to, it's a binary protocol, so it's like only it could just be based on obviously much less efficient, but anyway, but that's 9p, so if you want to. So pretty much all is in here is 9p implemented in this receive request function. And I thought, well, it'd probably be pretty difficult to re-implement this. Looking at this, I was like, I don't know how it works. I've done 9p before, but I don't know how they've done it. But it turns out that they don't implement everything here. They actually wrap their own file system abstraction. So if we go through here, there's a bunch of most of these things. This is a read, and they basically hand that off to some file system. Read. See, there's a bunch. There's write. There's rename. There's search, which is like walk. Unlink, which is like remove. And so then I found their file system implementation, all implemented in JavaScript. All of this is just to get that so that you could load files over HTTP. And this is all very specific to v86. So they implemented a file system, kind of a virtual file system, similar to what we've been doing, except because theirs is made for Linux, they actually model inodes as a Linux kernel thing. And this has a lot of stuff. Look at it. Handle event, load from JSON, load recursive, load dir. It's like, I don't know how many of these functions are part of a public interface, or some of them are capitalized, some of them aren't, but then I've seen them used all over the place in different places. So there's a lot here. So one idea was, I could implement file system, and then 9p would use that. Of course, file system looks even more complicated than just the number of messages that this 9p thing. But because of that, actually, I realized the surface area of the API that their 9p stuff uses is a little simpler. There's maybe, I don't know, a dozen methods that are called on FS. So I don't know what they've got going on here. I didn't want to try and do all of this from scratch. So I subclassed it. Created a JavaScript, prototypical inheritance. So Linux Wanix FS, basically inheriting from their file system. And then I ended up patching things because we need to do things async, and they weren't. But for the most part, whenever there's an async method, we're just wrapping theirs, but we can hook in. So there are two places where we're hooked in. One is open inode. So pretty much anytime it interacts with a file, it calls open inode. And so the other problem architecturally that we had to deal with is that this file system assumes that you have all of your files up front. That's why this fs.json file exists, because it loads the index of every file into memory. And then when it needs to read one, that's when it goes and fetches the file over HTTP. And this is so that it can save state and it'll have the state of the file system. But if we're bridging into Wanix, that's kind of like a dynamic file system. So we had to kind of, basically the plan is every time it requests a file, it will try and open it in Wanix, and then it will create an inode for this system. And so then it's sort of caching it in this file system. But constantly, every time you open it, it tries to get it again, so that it will, if the file changed or whatever, it updates. And then, of course, when you try and get the data, it will just read it. But yeah, the tricky part was just trying to get it to read from Wanix, and where to hook into. And there's really just those two places when you try and open a file. But of course, how does it know how to open a file that's not there? There's another feature of the file system called search, which is basically in 9p it's called walk, but basically, let's say starting with the root directory, what does this do? Basically, the first time it loads a directory. Actually, how does this work? Well, because it's whenever, like if I were to just type ls or open a file, it's going to first look up the parent inode, and then I wanted to open foo. And so it'll be like, foo, is there a foo in the file system? It's basically looking over all its inodes. And, if it's not there, then we just do a Wanix open inode. So this is calling into Wanix, looking for that file. And then once this is done, now there should be an inode in here. So we just call search again. And then in theory, it would have the file. So it ends up not being a ton of code, but this is currently just read only. So there's a little bit more work to support all the write operations. But this is enough to have gotten it to work. um, work with at least read the file system so far. Um, and that's kind of what I've been working on is getting that right, getting it to work with dynamic files and stuff. File system stuff is pretty tricky, but still more work to go since I do all the right operations. However, every time, and this is all just trial and error, trying to get something that works, and this doesn't work, let's try doing it this way. Every time I made a change and I wanted to try it again, I'd have to refresh the page and let that whole machine boot again. Remember, it took a while. I could make a script that would do some of this work. Create a VM, create the xterm and child, set up that binding, and then it would be as easy as just doing the right start. But we'd still have to wait for this boot. Usually with emulators and stuff like that, you can save the state. So that's how the V86 site was able to just instantly boot into Windows 2000 or Plan 9. It's basically already booted, then they save the state of the VM, and then they just load the state and it's available. And that's part of what we would need to do here. But where would we put that state? And I figured we could put it in OPFS. The origin private file system. It's on the page. The problem though was it didn't support write operations, and that led to a whole bunch of stuff with our file system API stuff in Go that I can talk about after a break. But basically, as a kind of a so talked about that. When we come back, I'll talk about how I added write operations and some of the problems with the abstractions that we made for building up file systems, how those kind of get in the way of doing adding write stuff, and how I solved that. And then also a custom Linux distro that we ended up making. It's really cool. And then if there's time, we'll talk about the roadmap of what next. But now I'll take a 5-minute break.
Sounds good.
I'm back. Where is Tara?
Ready whenever you are.
Okay. How's this going
Why'd
so
you
far?
laugh?
I was writing on the thing. Tara, where are you? Screen.
No.
Um. Yeah. I mean,
It's a lot of information.
yeah, I know, but if I don't, the whole idea of this series was to sort of like, oh, you could see a big build from scratch, but if I end up doing all this stuff off stream and share all this stuff, I mean, in a way, like all the hardest stuff is in the beginning. The whole point is you build these abstractions and things get.
Mm-hmm.
Um.
You have your file structures and stuff set up.
Yeah, and they all read and write and tools for building new ones and dynamic ones and yeah. So what's next? I was going to talk about this issue of creating basically a sort of a design problem with our file system abstractions. I mean, this comes back to this idea that this is all sort of building up on top of the file system interface that is now part of the Go standard library. File system now has a common interface in the same way that IO writers and IO readers have a common interface, and that creates this ecosystem where things can just kind of like work together nicely. But the Go interface for file systems is much more simplified than what you'd expect, because one, it's read-only, and it's just this one method open. But they gave some hints. I've talked about this before, where as a design pattern, you can implement open, and that's sort of the minimum API to be a file system. But then if you wanted to implement other there are basically extensions that you can have to a file system. So if you implement stat, instead of opening a file and then calling stat, you could then just call stat directly on the file system, which is a common thing. They did this as a interface extension. And same with like read file and a couple of other things. Sub we'll come back to, where sub is sort of like, give me a file system that represents a subdirectory of this file system. Basically, go into this directory and then give me a file system looking thing that's sort of rooted at that directory. So, some examples of some methods that you could add to your file system implementation, and then you would use basically helper function instead of calling instead of calling subfs. Damn it. Subfs here. The idea is, your file system will have a sub method. Oh, well, now I have to type assert to subfs to get sub, especially if everything should be passed around as a file system, which basically means you just have open. Then you have to type assert it to subfs, be able to call sub. That's kind of annoying. So they have helper functions that doing normal conventions. So instead you'd call a function, on the fs package has sub, where you give it a file system and a directory. It effectively calls sub on it. It will behind the scenes do the type assertion, see if it implements sub, and that's sort of laid a way to add more to the file system. I guess the first sort of extensible Go interface system that I've seen. We built on that and implemented, a lot of the other things that you would need for a file system. Rename, remove, make dir, and we have helpers for all of these as well. And the nice thing about this is that when you implement a file system, which we're implementing lots of file systems here, you don't have to implement all of these methods. You can just implement the minimal amount that you need. And so far, a lot of what we've been doing, the file systems that we've made have been read-only. And I guess OPFS would be the first one that we could actually write to, because it's actually going to store it in the OPFS storage system. So to do a basic read-only file system, you just have to implement open, and then in our system, you also implement open context. But then here I implemented create and make dir and remove. And so in theory, I could use, these helpers. If I want to call remove, I'd say fs remove and then pass it the OPFS file system and then the file that I want to remove. Okay, the problem is that we're calling all of these operations, remove, etc., on, just to kind of revisit what are in the browser, what's going on. We're compiling this WASM Go module, and this is all still being cleaned up and stuff like that. But we have our Wanix kernel, which is very simple. It doesn't really do much. For WASM. It's just a data structure that points to a bunch of these built-in file systems or devices, sets them up, sets up some of the, registers some of the built-in stuff. We have this new root that basically sets up that empty process that we talked about. That gives us the namespace that we would then use to interact with this. We use bind, but through the Go API, to take all of these built-in file systems, which are similar to Plan 9, are actually exposed as hidden file systems, which is prefixing them with a hash so they don't show up. But this adds them to the namespace, and then that gives us root, but then we actually want to expose those. So we do bindings to bind, hidden fsys to fsys, et cetera. Similar to the JavaScript code here, where I'm doing some setup to set up a VM and the xterm and all this stuff. Right now in Go, it's actually setting up the OPFS, mounting it, and then doing a bind to OPFS. And then the way it communicates, WASM is sort of an isolated environment, but we can access JavaScript stuff. So we can get a global, and there's a message port. Is it a message port? Message port. No, message channel. And in somewhere, set that up. Set up a channel, message channel. Set up new Wanix. Basically just a wrapper that will call into our WASM stuff over the message channel. And then we a message channel is basically a two-ended pipe. So they have port 1. The one end is being used by our JavaScript client API, and then we take the other port and just post it up at window.port. That in our WASM compiled Go, we can grab that and then set up another end of duplex, which is what we use for all of these projects. Lets us multiplex byte streams and do RPC and stuff. So basically implement some RPC methods, open inode, read dir, make dir, remove. Most of these are just wrapping these commands. So remove. When we call our, these little helpers I made in the JavaScript console, they're all just shorthands for calling these methods, which are then all over RPC, calling into Go these, and then ultimately calling the fs remove, fs make dir, etc., using root namespace and whatever arguments we passed. So you'll notice all of these operations, for example, make dir, which is the first kind of write operation implemented, is make dir on the namespace. And a couple streams ago, we looked at namespaces. I don't think I implemented on stream, but we worked on them. So namespace, this is implementing the Plan 9 style file interface. The idea is a namespace is just, in theory, it's a file system, but it has nothing in it. Instead, you have to bind stuff into it. So it's empty, and then you would get other file systems, and then you effectively bind mount them at different paths in here, including you could bind mount root. As we saw, we bind, all the directories that we saw in there are the result of bindings. So a namespace is really just kind of like a thing that stores paths and then references into other file systems. It could be a subpath of another file system. And at any path in this file system, it could have multiple bindings. We could bind multiple things at the same path, and it will kind of merge them together. Very Plan 9. So all the operations we're doing are against file system, the namespace file system. And so far, we really just had to implement open, right, to make it a file system, an open context. And that was pretty much it. That would let us read directories and read files. I ended up having to implement stat to avoid an issue, because when we do an open, it actually kind of iterates over all the bindings, so all the file systems, and does a stat call on them to see, is the root a directory, and it does different things. And unfortunately, the way stat is implemented is normally it will call open to open up a file, and then you'd call stat on the file. But when we got into recursive stuff, like when you look at the namespace or process one, and that kind of loops back to the root, that would cause a kind of infinite recursion. So implementing stat on this that doesn't involve calling open in most cases sort of breaks that cycle. So far, our namespace just implements open and stat, and then bind. But the way our file system stuff works is that, okay, if we want to call make dir, then it needs to implement make dir, or remove, or whatever. And then this isn't the only one, because, most of the things that we're binding in here are, we've got like the our proc file system. Here we're implementing open, and in that we're using mapfs, which returns a file system. So that implements open and stat. And so there's this, and then union fs. So we're composing, almost layering these file systems out of each other, but because of the way Go interfaces work, every method that we want to add, we'd have to add to every one of those layers. So you could imagine, we'd have to add make dir to namespace, We'd have to add makedir uh, to mapfs. We'd have to add makedir to unionfs, and any other abstractions that we use that that we make to compose file systems would have to implement not just makedir, but any other method that could possibly be called on any file system. Then we're stuck in this situation where we have to implement all these APIs all over the place. So I finally found kind of a solution to this. Back here, so OPFS and just a reminder, fsys, oops. So in order to do an operation on the OPFS file system that's at this mount, like makedir, you have to do makedir on the namespace, and then the namespace would give us the file system device, and then the file system device is composed of, is a union fs of a map fs, etc. And so again, makedir would have to be implemented in all of those. Instead, we talked about this sub function, API, whatever, that gives you basically a file system of a subtree of a file system. And I had this idea that if we could use sub to kind of get to this sort of most inner file system, then the file system that we get back from that would have makedir and whatever else that specific file system implements. And it would kind of allow us to bypass any file systems along the way. And then we would really only need to implement instead of implementing all the methods on every file system, we would only need to implement all the methods on this subdir fs, basically what sub returns, which it will either return. Subdir fs is really if you're trying to get to a directory underneath a existing file system. All of this is doing is, when you call open or whatever, it's just taking, the directory and putting that at the beginning of the name that you're trying to open. You say open, and instead of being open foo, subdir.fs is set up with such and such file system, and we're in the bar path of it, so it would be bar foo. It actually does the open. So it's doing is sort of like keeping track of a name that it's gonna prefix to every operation. Pretty simple. But there's another problem, which is ideally we wouldn't even get this if the file system that we're referring to is the root of that file system. So anyway, this whole thing is set up so that if you can use sub to try and get a particular file system, and if it's a subpath of that most inner file system, you get a subdir.fs. If it's the root of that file system, it gives you that file system directly. And so in the case of our OPFS, we would get this file system back. And then we call makedir, etc. So that worked out pretty well. It took a while to get it right. And it does mean that all of these operations create, all these kind of extension methods. You do have to have quite a bit of code here, mostly to avoid infinite recursion. But for the most part, it's pretty simple if we ignore this part, right? The way these things usually work is, oh, you want to call makedir on this file system? Well, we'll do the type assertion to see, does it have makedir? It does, we'll call makedir for you. And if not, then we'll return an error, makedir not supported. And it's not just doing this type assertion that these things are doing for you. It's not just kind of syntactic sugar. For example, there's makedir all, because makedir will fail if any of the parent directories don't exist. And so if you implement makedir all, it'll use makedir all, but you can kind of derive makedir all with just makedir. It'll just have to manually go and create every parent directory along the way. So again, this allows you to implement less in your file systems and still get makedir all, remove all and stuff, because through these functions, we're kind of recreating that functionality. So now in most of these, we just have to do this one thing, which is, if this is if this name is a path, basically it's a, you're trying to do foo/bar. If you're just trying to make dir foo, then that's a file that's directly at the root of this file system. And so if this file system doesn't have makedir, you're out of luck. But, in our case, we're pathing into deeper and deeper. And so we check to see, hey, if basically, is this a full kind of subpath? And if the file system that we have, in this case, that would be the namespace at the top level, if it doesn't have makedir, we'll just try and call sub. And so we call sub to get the file system of the parent directory of the path we're trying to do makedir on. Now we have a file system that in theory, for example, could be the OPFS file system. And then we can basically call makedir again, which would do type assertion makedir fs. Yes, I have makedir, so it works. And then any of the file systems kind of along the way in that path are, irrelevant. We don't have to kind of like pass through all of them. Sub lets us do that. It does mean we have to implement sub on all of them, but that's a lot easier than implementing every method. And then lastly, this part is just kind of a technical thing where it's possible for you to get in a state where a parent is a subdir fs, and then we call makedir on it. I forget how it works or what the case was, but basically the way to get through that was if parent is a subdir fs and the file system for that subdir fs is file system that we're calling makedir on, then we won't do this because it'll basically recurse in some situation. So instead, we just manually do the same thing that we did here, but here, and that just allows us to avoid that recursion. Kind of silly. Now we have to kind of do that for pretty much every operation. So remove looks very similar. again, to avoid the infinite recursion. Probably wrap this up into some kind of generic helper. But for now. So anyway, that got us these kind of write operations on the file system without having to implement those methods everywhere. That's another thing I did in the last week. And that got us, again, writer operations on OPFS. And the idea was to then use that to save the state from our VM so it doesn't take so long to boot while I'm trying to debug this bridge file system and make it work. And I have to wait for it every time I make a change. But then in parallel, there was this idea that we could, well, first of all, now we're getting to the point, we're getting closer to, hey, Wanix has everything it needs to kind of bootstrap itself into an environment that you can then, that it can then operate on itself. But we have to package, v86 with it and a Linux environment. It turns out, though, that this image that we're working with is just the file system files. 344 megabytes. Now, all our work of using TinyGo to get our kernel down to like 2 megabytes. Well, it doesn't matter if we have to package it with this giant image. It's even more if you include the save state that you would want so that it boots up really quick. Like that, I don't know. There's ways to optimize it, but in total, like this whole image on disk is, almost half a gig. And it's kind of weird because it's Alpine. It should be a lot smaller. We had this issue with Docker, the idea that everybody was making initially with Docker, everybody was using Ubuntu as the base image because everybody thought, hey, I know Ubuntu. But Ubuntu, and they made this way better, but back then Ubuntu was also about half a gig just as a base system. They've somehow got it down and compressed it to bare minimum 30 megabytes, something like that. But at the time, I had discovered Alpine Linux. And Alpine Linux is only 5 megabytes. Compressed, it's even smaller. And again, Alpine is actually what we're using here, but it's, for various reasons I won't get into, it's much larger. But in theory, this is why I popularized Alpine in the Docker. I ran the original Alpine Docker Hub repository and then handed it over to Docker to be the official repository for Alpine, because I don't know why Docker proper company took forever to realize that, hey, Alpine is a better, smaller base image to use for everything. So I've kind of been through this before. The way this works, Alpine Linux is a combination of, it's basically BusyBox plus their own package manager. That kind of makes it Alpine. BusyBox is this thing that's been around for a long time. When you build a Linux system, it's, besides the Linux kernel, the file system you need, the root file system that you need to build, doesn't need to have anything in it, but you can't do anything in it because you need to have all of these commands. You need to have a shell, you need to be able to do copy, rm. Some of these commands will often be built into bash or whatever shell you have, but there are so many utilities that you need, sometimes, often separately installed. So BusyBox came along whenever this was, initial release in 99, 25 years ago. But basically it's a single binary, single executable, and it's pretty small. about 2 megabytes, and it has equivalents for all of these. So it basically gives you all of these commands. It even has a shell called Ash, kind of bash like. So besides the kernel, you need a bunch of utilities. So with BusyBox, you kind of have everything you need in this tiny little binary. And that's literally what Alpine is BusyBox, plus some other stuff. They decided for whatever reason to use a particular glibc, which is a standard library. Different implementation than normal one. It's called Muscle, and all of their packages are built on it. So really, to me, Alpine is their package library. That's the reason why I was into Alpine as opposed to making a custom image with just BusyBox, because just BusyBox, how do you install new software? So Alpine sort of adds, I guess what makes Alpine great is that it has an amazing package library. Almost everything you would want to install is in their package library, and it's kind of minimalistic since it's designed for a system with just BusyBox. And important for us is they also have packages for 32-bit architecture, since v86 is currently just 32-bit. So, yeah, that's pretty cool, and it's pretty much just Alpine. But the thing is that Docker is not just the nature of Docker is you're using the Linux kernel of their host system. When we're running a VM, we also need the Linux kernel. Linux kernel is usually, 10 megabytes. So the theoretical minimal Linux distro would be the Linux kernel and a file system with BusyBox. Okay, that's like maybe, 10, 12 megabytes. But you can do custom builds of the Linux kernel. The Linux kernel has accumulated all of these drivers and support for all of these CPUs and all of these devices. We don't need most of those because we're always running it in this v86 environment where it's always the same stuff. So you can actually customize the Linux kernel. And a little while ago, I saw this video called Making the Smallest Possible Linux Distro, in which they just did a custom build of the Linux kernel. They basically turned almost everything off, and they got it to 781 kilobytes. So just, that's, obviously less than a megabyte, but 3/4 of a megabyte, I guess. And then the rest of this video is them making a shell, a really minimal shell by hand, which is kind of silly and pointless. But anyway, I was inspired by, we could make a minimal kernel. So I'm not a Linux hacker. That sort of intimidated me. But I worked with Claude, with, AI, and was able to come up with something. So this is a separate project called WTux. So it's made specifically for Wanix. And it just builds it all in a Docker file, but then it gives you a kernel and a BusyBox. And we've got it down to 3 megabytes for the whole thing. I think we can get it even smaller. That's cool. Let me show you what that looks like real quick. We need to swap out our b86 config here instead of doing this. We'll do this. um, which is just our custom Linux kernel and a tiny initramfs that basically just has busybox in it. Again, together those files are about 3 megabytes. Okay. Whoa. We didn't see any kernel boot stuff or anything, mostly because that would, one, writing all of that to the terminal would be slow because of the whole byte by byte thing. But also, even if you did see well, we can actually see the whole boot process if I add this other way to see the output of this. So this is kind of a direct console to the v86 VM, and then this is our terminal. Start. So that was the kernel boot, which was a lot faster, actually doing a lot less, because it doesn't have to go through all the stuff that it would normally check to see that it has installed. It doesn't have to do that. So it turns out this boot's a lot faster. It's like a couple seconds compared to like 30, 40 seconds before. So it almost is fast enough that we don't have to save the state and restore state, at least for this like built-in Linux. There is a little bit of a delay here before we get the prompt, but it even, puts us directly into Wanix, so we can just working with OPFS and whatever. So that's cool. That's kind of what I've been doing the last couple of days. So that pretty much brings us up to speed. And like I said, we could actually get this a little bit smaller. But the great thing is now, and this is one reason, hopefully I've explained lots of reasons why we did this. We're doing this rewrite for Wanix. All this capability that we get out of just having file systems and having namespaces and all that stuff. We actually haven't even shown all the benefits of that yet. But one benefit is in the original Wanix that that was being demoed here. There was the kernel, there was our shell that we made, and an editor, and a compiler. The kernel was 22 megabytes. The shell was 13 megabytes. Right? Altogether compressed was 65 megabytes. We won't embed a compiler with it now, but now our Wanix kernel is 2.6 megabytes. v86 is 2 megabytes, and our custom Linux kernel is 3 megabytes, which compressed 4 megabytes. We went from 65 megabytes to 4 megabytes. And this version can run x86 executables. So that's one reason why we did this rewrite. That's almost all of our time. So that was a lot because there's a lot of progress since the last stream. Usually I want to try and work on it on stream. So we'll kind of get back to that with the next stream. But this felt like a good time to just kind of go over everything. I had to go over so much anyway. One thing we could talk about is what next. I mentioned we have save and restore interface for the VM. Finishing write operations so we can actually do everything we've been doing over here from this environment. Also, so far, there aren't any actual process types. The VM is just kind of running outside of Wanix, but the idea is we want to add a web worker process type. And then when you start the VM, it will actually run that as its own Wanix process in a web worker. Um, and then we can also get into supporting WASI executables, actually running native WASM programs. And you'll be able to run them in this Linux environment because we're just kind of merging these Wanix and Linux in a way. And then creating more of a interface around the VM that lets you kind of do a lot of NV86 stuff where you can create images, almost a Docker-like environment. And so you'll be able to not just run, this Linux made specifically for working with Wanix, but you could run custom Linuxes. I mean, you could run Windows because it's 86. And that way Wanix becomes almost like a hypervisor, except it's 4 megabytes and runs on the web and also runs on every platform. Wow, I've never seen anything like that before. Um,
Wow.
yeah. And then finally, we can get VS Code running in it. And that's when we'll cut a 0.3 release. And it would be able to do almost everything that we did in this demo, although it won't come with everything. I guess we could port some of the stuff to the new system, but yeah, it'll be this crazy new thing. And in theory, you could build stuff. So we would use this as a kind of a operating system, quote unquote, operating system or kernel for things like Aptron, which is where we originally used v86 to create and I don't know what state in, but so this is v86. This is actually the same image that we're testing Wanix, but this can also access the network and install custom packages. This is a full Linux environment running in the browser. There is no, so this in itself is an innovation. A full Linux development environment in the browser that you can, in theory, open, get repositories in here, work on them, commit them. I've made changes to my static website from this. And like a lot of these, like Gitpod, code spaces, they let you define a custom environment, kind of like a Docker file. So that this project has this environment. This project has this environment with these things installed. We can set that up by building on top of Wanix and developing the Wanix VM stuff. We can create a Docker-like system so that we can, on the fly, create those different development environments. And so you could use Aptron to, like a cloud IDE, except it's running entirely in the browser, so it costs nothing for us to run. But if you wanted, you'd be able to go into Wanix and do cool Wanix hacking and customize this environment or do other VMs. I have no reason not to hide that from, advanced users to potentially customize their work environment for a particular project to do whatever they want. And then getting into using this VS Code environment to edit VS Code from the environment. You have a live programming environment. It's malleable software. You could customize it, create new extensions to the VS Code that you're using wh- while using it, um, and it would all be built on. So that's another kind of motivator for Wanix. But there's a lot of other cool stuff we can do with Wanix, so that's why it is its own thing. Whew. At least I got it all in 2 hours.
Yeah, it is impressive.
Um, you were pretty quiet, I guess.
Well, it's
Any
also hard to
questions?
know, like it's hard to know when to interject, like,
Yeah, I'm on a
you
roll,
often get going, yeah. I don't
but
wanna, like, interrupt you.
I think you should interrupt if there is something. Um, can you think of anything that you would have wanted to interrupt about?
I mean, mm, no, it's also, like, hard to know how much I should be trying to ask questions and understand this because it is, kind of above my.
Yep. But I mean, you were able to follow it at a high level,
Yeah,
so that's good. At a high
yeah.
level, were there any confusing parts to it?
Nothing I can think of really.
Well, that's good. I did a no job. It was adequate.
Yeah. Yes. You're adequate for sure.
Okay. Um, I guess tomorrow we'll work on TerraGen, and then we'll work on this more. Actually, work on it on Wednesday, and Friday there is the Plan 9 watch party. So if you want to learn more about the integration, come to our Discord.
Oh yeah, should I find that? Can I never find the link? Okay, I'll post the link in the chat.
Because I cannot. It breaks the link. I'm in streamer mode.
Yeah, that's weird.
I guess that concludes our stream for today.
Nice. Good work.
Um, yeah. Uh, goodbye, everybody.
Bye-bye.